Okay, so we left off with uh, the budget constraint, right? And basically, I said it was a straight line that maps the amount of good one and good two you can consume uh, by exhausting your budget, right? So each each point along this line is a consumption bundle that will max at 180 grams of carbs. Or if it was a dollar amount, let's say it was each beer cost you $2 and each samosa cost you $1 and you had $10. This could be like or whatever. This will be the amount of beers that maximizes your budget constraint when you consume zero samosas. This would be the amount of samosas that maximizes your $10. So this would be 10. This would be 2 if it was a dollar amount. But at any rate, this is all the combinations of consumption bundles that will maximize your budget constraint. Everything under is a consumption bundle that will not maximize your budget constraint. Everything over is a consumption bundle that will be out of your budget. So things that you cannot consume. So similar to the PPF in the sense of, this is everything in here is feasible and inefficient. Everything on the line is both feasible and efficient, and everything above is infeasible. So, look at the axes, right? It's beer and samosas, just like with the indifference curves. So we can actually plot indifference curves going through this budget constraint. So let's say that's one indifference curve, and that utility is equal to x. Okay. So every combination along of beer and samosas, every consumption bundle along this red line gives you a utility of x. Okay. And every consumption bundle along this blue line gives you a utility of y. And every consumption bundle along this purple line, sorry, I want to undo that for a second for reasons I will explain to you later, or in close time. So everything along this purple line, which is not really parallel, but whatever, it doesn't exactly have to be as long as it doesn't touch, is a utility equal to z. So we have different indifference curves. Different indifference curves, that actually sounds kind of funny. We have 3 indifference curves running through running through the budget constraint. Okay, this is another reason why I hate distance learning. I could not use the whiteboard, which sucks. I love the whiteboard. We have 3 indifference curves running through the budget constraint. Okay, and what do you know about X, Y, and Z? Well, Abby likes both beer and samosas. So what can you say about X versus Y? Well, you can say that Y is greater than X. Abby would rather consume more beer and more samosas than less beer and less samosas, right? So going from this point to this point, Abby is consuming the same amount of samosas, right? But he's consuming more beers. And those extra beers net him extra utility, right? So he's going from utility X to utility Y. So you can definitely say that Y is greater than X. Okay, so more beers is preferred to less beers. And because more beers are preferred to less beers, Y should be greater than X. You get more utility from consuming more beers than you do from consuming less beers. Okay, so Y is greater than X. You can also make for the same logic, you can say Z is greater than Y. And because we assume that preference is irrational, we can say that Z is greater than X. Okay. So that's part of the rationality assumptions that I kind of talked about last week, that you have stable preferences and they're transitive, so you can compare Y to X and Z to Y. So as long as Z is greater than Y, you can say, as long as Z is greater than Y and Y is greater than X, you can say Z is greater than X. In the real world, it's not always the case that you say that. But in order to say anything meaningful about anybody's preferences, you should be able to say that they're transitive. So we abstract and we say that 99% of the time preferences will be transitive. So let's make it definite and say 100% of the time preferences are transitive. If you prefer pineapples to oranges, and you prefer oranges to apples, you should prefer pineapples to apples. But some people are weird. So anyway, z is greater than x. We can say that for sure. And z is on a higher indifference curve because we prefer more beer and more samosas. So going away from the axis should be higher indifference curves. So like going up should be higher indifference curves. Or higher utilities, rather. So basically we have this budget constraint, right? And we have 3 indifference curves running through it. So we can say at this point, let's call this A, B. This point here, call it C. This point over here, call it D. And this point over here, you can call it E. A, B, C, D, and E all exhaust the budget constraint. In fact, I want to do this on whiteboard so that you can see, so that you can reference it in your notes. So let's just do this real quick. Actually, I have it already drawn. Let's redraw it. So we have S, right? Samosas at the bottom. And we have B up top. And this is like 5.625. Geez, that's hard to read, but that should be oh, I'm making it worse. Should be 5.625. Samosas and 4.5 beers. Then we have a line. Okay, and then we had 3 indifference curves. And then we had point A. This is point A. This is point B. This is point C. This is point D. And this is point E. Okay. So what can we say about the utility of A, B, C? Oh, also, so utility equals X. Utility equals Y. Utility equals Z. We said that Z is greater than Y is greater than X. Okay. So what can we say about A, B, C, D, and E? A, B, C, D, and E are all points that lie on the budget constraint. What does that mean? Well, I'll tell you what that means. I'll say format, AKA, all 5 points exhaust your budget. Okay, so if you have 180 grams of carbs, you could get that by consuming A, consuming B, consuming bundle C, D, and E. Okay, so they're all, I want to actually specify, they're all but points, I'm going to say consumption bundles that lie on the budget constraint. All 5 points exhaust your budget, right? So at this point, you're exhausting your budget. At this point, you're exhausting your budget, right? So you're at all 5 points, you're consuming 180 grams of carbs. Just there's different combinations between the 180 grams of carbs. So this one has a lot of samosas. This one has a lot of beer. This one has a mixture between samosas and beer. What can we say about their utilities, though? What about A versus B? Well, A and B both lie on the same indifference curve. A and B lie on the same indifference curve. All right, and what does that mean? What does it mean to lie on the same indifference curve? Think about it. They have the same utility. So if I asked you to pick between A and B, you'd be like, I don't care, whatever, it doesn't matter. They give me the same amount of happiness, right? So you don't care between A and B, same utility. That's why you're indifferent. That's why they're called indifference curves. You're indifferent between A and B. What about A or B versus C? Question mark, question mark, question mark. Which do you prefer? Well, you should prefer C because it's on a higher indifference curve. I'm going to use IC for indifference curve. So you prefer C to both A and B. What about C versus D? You don't care between C and D. C and D net you the same indifference curve. Okay. What about C or D versus E? Question mark, question mark, question mark. For the same reasons that you prefer C to A, that they're on a higher indifference curve, you prefer E to C or D. Okay? Because C and D both get you Y utility, but E gets you Z utility. So Z is a higher utility function, or a higher indifference curve. Okay? So at all points A to E, you are spending all your calories. But your highest utility at E. So you should consume at E. Obviously, you should consume at E, right? If you're out of money or out of calories at C, but you're not as happy as you could be, obviously you'd want to be happier, right? You want to get a higher utility, so you consume at E. Okay? So E is the best way to consume. So we can say consuming at E is better than consuming at A through D. Is there another way to consume? Is there another point at which you can get happier without going over budget? So the way I drew it, no, there's no way to get happier, because E is the only point. It's kind of hard to see how I drew it because I suck at drawing, but E is the only, I wish I could underline that or something. E is the only point on that indifference curve that touches the budget constraint. If it weren't, well, it would touch at 2 points. Right, so D and C, A and B, right? If you draw a straight line between a curve like this, it's going to touch at 2 points. Okay. So what we call that, and I've used this word before, but we call that the tangent point. So the tangent point is the point, a point that touches another line at only, sorry, should be one, it's the point that touches the curve at only one point. I don't know how to say that. Tangent means touching at only one point. So a tangent line from E would be the budget constraint. So you, aka, you can say the budget constraint and the black utility curve are tangent to each other. They touch at only one point. Okay. Alternatively, you can say that E is a tangent point to the budget constraint, or that the budget constraint is tangent to the black utility curve, black indifference curve at E. Okay, they're all saying the same thing. I'm going to bring this note down here now that we're done with it. Okay. So to answer the question, no, there is no other point at which you can consume that will get you a higher indifference curve. Because we've basically taken it as far as we can, and we're only touching at one point now. So that is the highest utility curve you can get that's still on the budget constraint. Okay, otherwise it would touch at 2 points like C and D. Okay. So E is tangent to the budget constraint, or the black line is tangent to the budget constraint at E. The black indifference curve is tangent to the budget constraint at E. Okay. So when we were talking about marginal utility, right, I mentioned that if I have an indifference curve, right, I think I drew it up here somewhere, right? Ah, no, oh no. I think I drew it up here. Yeah. So when we were talking about marginal utility, and I messed up the formula and I had it upside down, but when we were talking about marginal utility, I talked about how the slope of the indifference curve, like tangent at any point, is the marginal rate of substitution, right? The slope of the IC is equal to the marginal rate of substitution is equal to MUX divided by MUY. Call that marginal rate of substitution X for Y, and that is the amount of Y you give up for 1 unit of X. Okay. So I mentioned earlier that the slope of the indifference curve at any tangent will give you your marginal rate of substitution. Okay. At point E, right, we can say the slope of the IC is MRS sub XY, or MUX divided by MUY, right? The tangent to the indifference curve. What else is tangent to the indifference curve at point E? Right, I just spent time talking about this. So at point E, the tangent to the indifference curve is your budget constraint. Gee whiz. That's funny, isn't that? So what does that mean? At point E, your marginal rate of substitution is equal to the budget constraint. specifically the slope of the budget constraint. And if we're thinking about the slope of the budget constraint, we're thinking about the price of each good in this case in terms of calories. So for the sake of explanation, since I'm still on this graph, let me bring this over here. I'll bring it back down when I'm ready to do the notes, like when I'm compiling the notes for your reference. So at point E, the marginal rate of substitution is equal to the slope of the budget constraint. In this case, it'll be 180 grams equals 40 grams times beer plus 32 grams times samosas. Beer is on the x-axis. Samosas on the x-axis. So we want beer. If we were writing this in slope-intercept form, 40 grams equals 40. Let's just say 40 times b, for the sake of simplicity. 40 times b is equal to 32 times s minus 180. Okay, so I'm just rearranging this. Since beer is on the y-axis, I want this in slope-intercept form. So the y-axis good is b, 32 is s is going to be the x-axis good. So the slope, that's not the slope, but the coefficient of the amount of samosas is going to be 32, and then this is going to be your constant of 180. So I'm going to subtract this from both sides. Subtract samosas. Sorry, I had this backwards. So I'm going to subtract 32 grams of samosas from both sides. So negative 32. So 180 minus 32 samosas is your is on the one side, and then 40 times b is on the other. So then, if we want it in slope-intercept form, we're going to divide both sides by negative 40. So we have negative 32 divided by 40. S plus 4.5 is your slope-intercept form. Okay. If you wanted to double check this, look at the slope is, the intercept is going to be 4.5, right? And the slope should be 4/5 if we were to simplify this. If we wanted to do the math on that, so we have rise of 4.5 minus 0 divided by run of 0 minus 5.65. My calculator at, let me do one more step. 4.5 divided by negative 5.625. 0.625. 4.5 divided by 5.65 should be 0.8, aka 4/5. So we know we're right. 4/5. Okay. Okay, 32 over 40. Then negative. So the slope of the budget constraint, if you haven't noticed, would be the price of the x-axis good, samosas, over the price of the y-axis good. Where price in this case is calories. Price of the x-axis good over price of the y-axis good. Okay. Sorry, I realized I'm zoomed in a little bit. So let's bring it all back for a second before I move any further. We started with a budget constraint. We said that we can plot indifference curves that will cross the budget constraint and exhaust all the budget. But only one of those indifference curves lies on the highest possible line. Hey! Sorry. My cat was misbehaving, and I need to stop him from doing something that he shouldn't be doing. And it's too long in the lecture to restart. Excuse me. So, what I was saying is that we plotted we started with the budget constraint. We plotted a bunch of indifference curves, which could be, arbitrarily defined based on some level of utility. But only one of those indifference curves is going to have a point that is tangent to the budget constraint. Okay. I.e., only one of those indifference curves is going to cross at only one point, is going to cross the budget constraint at only 1 point. 1 point. That point was E, right? So this is the highest possible indifference curve you can have that's still touching the budget constraint. Okay? And we can say at point E, if you were to draw a tangent line, or at any point on the indifference curve, if you were to draw a tangent line, the slope of the tangent line will give you your marginal rate of substitution, the amount of samosas that you need to give up for one beer, or vice versa. Okay, so in this case, it'll be the amount of beers that you need to give up for one samosa. Okay, the marginal rate of substitution, alternatively, can be quoted as the marginal utility of beers divided by your marginal utility of samosas. Okay, but at E, we can say that the marginal rate of substitution, which is the marginal utility from beers over the marginal utility from samosas, is the same line as the so it's going to be tangent. So it's going to be the same line is going to be tangent. Sorry, let me restart that. At E, the marginal rate of substitution, which is the tangent line to the indifference curve, is also the slope of the the budget constraint, which is the ratio of prices. Okay, so if you were to draw a tangent here, it's going to be tangent to the budget constraint. It's also going to be the marginal rate of substitution. By definition, marginal rate of substitution is going to be the slope of the tangent line at any point. Okay, and since we know that at E, the budget constraint must be tangent to the indifference curve, then the marginal rate of substitution is equal to the slope of the budget constraint. And we just found that the slope of the budget constraint is the price of X divided by the price of Y, or 32 divided by 40. Okay. So we can say at the optimal point, E, marginal utility is equal to PX, marginal rate of substitution. And I'm going to throw in a negative here because I forgot it here. Marginal rate of substitution is equal to your negative PX divided by your PY. Okay. And we know that marginal rate of substitution is MUX divided by MUY. Marginal utility from X divided by marginal utility from Y. Let me get my big old head out the way. Move, head, get out the way. A little bit of ludicrous for you guys today. So we have this relationship. Your negative prices divided by your negative utilities. Okay? Marginal utilities. Or divided by your marginal utilities, not negative utilities. Your negative prices divided by your marginal utilities. Okay. Alternatively, if we were to divide by each other, let's say we divided both sides by px and multiplied both sides by, so divide, oh, my head's still in the way. That's better. Divide both sides by p sub x, multiply both sides by mu sub y, we get mu y divided by py, I'm going to do lowercase for no reason, is equal to MUX divided by PX. Okay? And here's how I like to think about this. Okay? This, I think, is the simplest interpretation for me, at least. So every unit of consumption brings me some level of happiness, right? That is my marginal utility, the amount of happiness I get from consuming the next unit of samosas or the next unit of beer, right? It also incurs some sort of cost. So 32 grams of carbs is my cost of the samosa. 40 grams of carbs is my cost of beer. Well, if I'm consuming samosas and beer, I damn well better be getting some sort of bang for every unit of carbs that I'm spending, right? Some level of happiness for every unit of carbs. And since my since my price for beer, 40 grams, is higher than my price for carbs by a rate of 40 divided by 32, it should be 5 over 4, 1.25. Well, I better be getting 1.25 units of happiness for every unit, 1.25 units of happiness from the beers for every unit of happiness that I'm getting from carbs. Okay. AKA, if the price of the price in carbs, if a samosa is 1.25, if a beer 1.25 times the carbs of a samosa, it damn well better give me 1.25 times the happiness, right? I want the same bang for buck that I get from a carb of beer than I do a carb of samosa, right? For every carb, basically, I want to equalize the amount of happiness per carb. Equalizing the amount of happiness per carb. And it could be dollars. And that's what you'll probably see going forward. But I just don't like restricting to just dollars because I feel like that leads to people thinking that economics is about dollars. But really, economizing can be across multiple budget constraints. Okay, economize time, economize dollars, economize calories, economize whatever. Okay. All right. So, what if a beer gives me 1.5 times the happiness? Okay, aka my marginal utility for a beer is 1.5 times my marginal utility for a samosa. But the price is only 1.25 times the price samosa. So if my marginal utility for a beer is greater than my price of if my marginal utility for a beer is 1.5 times the marginal utility from a samosa, but the price is only 1.25 times the price of a samosa, what does that mean I should do? It means I should consume more beers and consume less samosas so as you consume more beers, right, what happens? By the law of diminishing marginal utility, the marginal utility will eventually go down, right? Consume more beers, right? That's the short answer. When I consume more beers, Geez Louise. When I consume more beers, what happens to my marginal utility? MU decreases. So I should say MU for beer decreases by the law of this. Sorry, y'all. It's getting too big. My marginal utility decreases by the law of diminishing marginal utility. And in case you forget what that is, let's go back up. Let's review the tape. Right? So here's my marginal utility from beer. As I consume more beers, I go further along on the x-axis. The change in the y-axis decreases. My slope of the utility function decreases. Okay, so my marginal utility decreases. Okay. No. That was dramatic, sorry. All right. So if I stay on the same budget, and I consume more beers, that means I have to consume less samosas. And what does that do? That means I consume less samosas, so my marginal utility is actually going to increase. MU samosa will increase. So I will keep consuming beer until MU beer divided by the price of beer is equal to MU samosa divided by the price of samosa, aka MU beer divided by MU samosa equals P beer divided by P samosa. Different ways of saying the same thing. These two equations are equivalent, which I just showed, right? But at the end of the day, the marginal utility from beer should get you the same, or the amount of beer you consume should get you the same bang per buck as the next beer you consume should get you the same bang per buck as the next samosa you consume. If your marginal utility for beers is greater than your price ratio, or if your marginal rate of substitution for beers is greater than your price ratio, then you should consume more beers. The marginal rate of substitution for beers is less than your price ratio, you should consume more samosas. All right. So let's put this all in order. Oh boy, that's a big old note, huh? There you go. Plop right there. Let's get back to the slides for a second. So it's optimal to consume at the point of the budget, the point where the budget constraint is tangent to the indifference curve. We showed this with point E, right? Point E is tangent to the indifference curve. Oh, hey. It's touching at only one point. Okay. If not, if the budget constraint can intersect with 0 points, which I guess I didn't show, but that would be the case where the indifference curve lies above, or with more than 1 point. If it's 0, that means it's infeasible. If it's more than 1, that means you can go on a higher indifference curve. And that all leads to this rule where the marginal utility of beer divided by the price of beer is equal to the marginal utility of samosas divided by the price of samosas. And they call it in the book the rule of equal marginal utility per dollar spent. That's like the technical econ term. I like the bang for buck rule because it's concise and to the point, which in general is everything that I'm not, but it's easier to understand. So bang for buck rule. The next beer better give you more happiness, or better give you the same happiness per dollar that the next samosa gives you per dollar. And then the other part of that is you got to exhaust your budget constraint, right? So technically speaking, if I had I don't want that. if I had a point here, let's call this F. Oh, Jesus, I cannot write to save my life. Yeah, let's add a point F. Maybe not F. Let's draw it differently. I wish I could copy this whole thing. So I just want to explain this one more thing. So here's E. I bet you guys love watching me draw and redraw graphs all the time like this. It should be mandatory for econ professors to go to art school or like some like level of art or something like that, because I cannot draw for crap and it shows. All right, so I have E, which is tangent to the budget constraint, right? So I have an indifference curve. And I want to draw a tangent at point F. So this tangent so let me actually label everything. So S, B, this is the budget constraint over here. This little red line is the budget constraint. And I want to, what would the slope of the budget constraint be? Well, you could say it two ways. Mu slope equals Px divided by Py, aka slope equals Mux divided by Muy. Right, we just showed that like 100 times. So if you don't understand why, go back and rewatch this video. Okay. This other red line is just a tangent with the MRS, a tangent at, let's say it's a tangent at point F showing the MRS at point F, okay? And at this point, the red lines are parallel, aka the slope of the MRS is equal to Px divided by Py. Okay, so this is just like a random point on a random indifference curve. Say a random point F and a random indifference curve that happens to have the same slope. Okay. That happens to have the same slope. So tangent at random point F showing the MRS at point F. At this point, so let's say point F, just by the fact that eventually you're going to have the same slope on an indifference curve, right, as is the budget constraint. So at point F, it happens to have the same slope as the budget constraint, aka the marginal rate of substitution is given by Px of Py. So this actually will satisfy the rule that I call the bang for buck rule, right? The equal marginal utility per dollar spent rule. So at this point, we can say this is true. Come on, I just want to highlight, geez Louise. So at this point, this is true, right? MUy divided by Py equals MUx divided by Px. Point F satisfies this. Does that mean point F is an optimal consumption bundle? Does it maximize the utility given the budget constraint? Is it the most happiness you can get given your budget constraint? What do you think? Is point F as happy as you can get given your budget constraint? Well, no, right? Why not? Because at point F, I can consume more beer and more samosas and go to point E, which is a higher indifference curve. No. At point F, I can consume more and go to E. I can go to other points too, which have higher indifference curves, but E is the best one. On a higher indifference curve, higher utility. So why can I do that? I can do this because I did not exhaust my budget constraint. So point F is feasible, but you're not exhausting your budget. So you can consume more of both goods, go to a higher indifference curve, get a higher utility. Okay. So that's why I add this little rule here. Where'd it go? Exhaust your budget to maximize utility. Okay. So your optimal consumption bundle will be like right there. All right. So that's it for lecture 8, part 1. I'm going to move into more indifference curve stuff, particularly perfect complements, perfect substitutes, and we'll go from there. All right.